Hello, everybody. Welcome to the next Dante webinar here. We'll get started in just about a minute, give people a chance to get in. Okay, I should give them some people time, and we can get started right now. So I'm going to go ahead and share my screen here. And then go ahead and go to presenter. There we go. Okay, so today we're talking about the effect of material and process variability on lower hardenability steels. Again, thank you for attending, and I hope you guys find this valuable. We're going to do a little bit of an introduction here and a little bit of introduction to Dante modeling. And then we're going to get into the material and process variability. For the material variability, we're going to use the DI and the Jominy calculations and the utilities that we have for those. And we're also going to show that variability with the alloy composition on the TTT and the CCT diagrams. Then we're going to look into the process variability with HTPSim, and we're going to look at quench severity, quench temperature, and transfer time. And then we have a little bit of a case study on chemistry changes in a carburized 8620. While not really a low hardenability steel, it still shows some interesting results that we want to talk about. So a little bit about us. We're your Dante Solutions. Dante stands for Distortion Analysis for Thermal Engineering. And we were founded in 1982 as Deformation Control Technologies. And we were focusing mainly on modeling thermal processing of metals. Dante Solutions has been focusing on the heat treatment simulation since the early 1990s, where we were part of a large collaborative effort between industry, academia, and the national labs to predict distortion in heat-treated steels. And that ran from like 92 to 2000. And that's really where the Dante software was born. It started out of a need to control distortion and reduce scrap in the industry. We've since gained sole ownership of that software that was developed, and we've been updating it and adding new features and stuff since then. Our main lines of business are software licensing. We do heat treatment technology development, where new emerging technologies where we can model and simulate. And then we do a lot of consulting services with our software. And you can see most of us here in the headshots. So we have a couple of new hires we got to add on to the list here. And we're located in Cleveland, Ohio, really close to Lake Erie. So heat treatment modeling basics, there's a lot that goes into heat treatment. So we're going to try to be brief and concise here. So the main three things for heat treatment modeling is heat transfer, the deformation that you get out of it, and then the phase transformations. But all these are interlinked. Like heat transfer, you have your temperature-induced transformation. As you can see with this little dialtometer animation at the bottom, we have a transformation to austenite out in heating, and then there's a transformation here for quenching, probably not cooling, quenching for the martensite transformation. And you can see that temperature-induced transformation is really the whole crux of heat treatment. As that phase transformation happens, there's also latent heat, so that goes back into the heat transfer calculation for a little nonlinearity there. As far as the phase transformations themselves, they have a volume change. You can see the austenite has a volume reduction, and the martensite here has a volume increase. And so those volume changes create more deformation. You could also go the opposite way here and have a stress-induced transformation where you physically deform it, and that creates the transformation there. And then lastly, the heat transfer and the deformation are linked here through thermal expansion. You can see again, with the dialtometer animation in the bottom there, you can see as the part is heated up, there is a coefficient of thermal expansion, and the part gets larger. And then on cooling, it gets smaller as well. But there's also heat generated from plastic deformation that needs to be added in with high strain applications, such as like hot stamping. So that goes all into the phase transformation models that we developed. There's also multi-phase mechanical models. So each one of these phases has different mechanical properties. So we need to account for all those. There's trip models, mixture laws, tempering models. We have a carbon partitioning model and other carburization and nitriding chemical process models as well that all go into this whole heat treatment simulation. So a little bit about our 3D software. We have a full package that's used. And you can see to the right here, kind of lists the tree of what we have when you get Dante. There's a user database that user materials, I'll talk about that here in a second. And then there's the stable version that we use with different plugins, examples, help documents, tutorials, and some generic HTC data for both Abacus or ANSYS, depending on how you use the full 3D software. But then there's also Dante utility tools, which are little snippets of the Dante code that we use to show different aspects. So whether you're doing a carburization, you can use a G-carb or a V-carb, whether you're doing gas or vacuum carburization. So each one of those little snippets we've kind of developed into utility tools, and a lot of these were developed to make our jobs easier, but then we realized that there could be a good market for it. So people are using those as well. These standalone tools, you'll see a couple of them today. We're going to use the DI predictor, the Jominy predictor, the TTT and CCT generator, and then the heat treatment process simulator, HTPSim, that you can kind of see here. You'll see more of those in a moment. Next, we have the Dante material database. The modeling of the heat treatment process prepares a lot of data, across large temperature ranges, in order to have an accurate model here. So we need the phase transformation kinetics, the plasticity mechanical properties, again, the coefficient of thermal expansion, and then the transformational strains that occur for each material, and then the hardness related properties like different phases and the iron carbide coarsening rates and stuff like that. So for the most part, we have pretty much a wide range of materials here. I think it was over 70 or so standard grades that last I checked. But we also have an expandable user database. So if we don't have something that you have, we can start from another material and then work backwards kind of to get the user material that you need. And this is all fully customizable by the user, so you can keep it, and that's your data that you can have. So if we don't have it, we can definitely work on getting it in the database. And here's just some commercial examples of parts we used modeling Dante. We did a scanning induction of an axle shaft. You can find a good case study of that on our website. We do a lot of gears, oil quench geared shaft, spur gears, bevel gears, and these have usually issues with the distortion that we need to control, and that's why we use our software to model these. Again, large landing gears as well. So this one really modeled the immersion quenching process, which is really important for capturing the bow distortion from this type of process. So let's talk about a little bit of heat treatment variability. So we're going to look today at 1020 steel and a little bit of variability between those. We're going to look at the DI calculation and the Jominy, like I said, and some CCT diagrams, and we're going to vary the carbon within that material range and see the effects that it would have on the hardenability of the steel. We're going to look at chemistry changes. Again, mainly for 1020, the manganese is the big change, the big lever you can pull there. And we'll also look a little bit at the austenite grain size calculation. Typically, larger grains are a little bit more hardenable. And then we're going to look at the process variability. We're going to look at heating and cooling rates. The quenching medium, we can definitely change that, or the agitation, level of agitation. A lot of times there's a different high or low agitation levels you can look at. And then the quench at temperature, we can look at the differences in those and as far as variability. And then a big one is also transfer time for a lot of materials, especially for low hardenability. The transfer time is really important. So let's get started here. So we're looking at we're going to look at the DI, also known as the ideal critical diameter. And the definition of that is the largest diameter bar that can be quenched to produce 50% martensite in the core. Now, the DI calculation assumes an infinite quench rate, and so we use just a really extremely high HTC on the surface in order to get our calculations. And then we can now go directly to the DI predictor. Oh, I just closed it. And we can open it up here. Okay, so we go right to the DI predictor tool. Luckily, these things open very fast. And we can start off with our material page. From here, we're going to select the 10 series steel, and we're going to look at 1020, so 0.2 carbon on the surface here. And you can see there's a bunch of different things that you can apply here: carbide size, LA precipitates, nitrogen and nitrides, and then the grain sizes. And then here's the chemistry that we tested in order to get our data in the database. So we'll just leave all these alone and just go ahead and analyze this. We are going to go and just drop this into the temp directory. DI 1020, and we will plot. And we can see here down at the bottom here, the ideal critical diameter from the base material here is about 15.9 or about 16 millimeters. So that means a 16 millimeter bar. If you were to quench it very quickly here, you should expect to see 50% martensite in that core there, about 16 millimeters deep. So with the calculation here, we can now start to look at the different changes in the chemistry. So the manganese can vary from 0.3 to 0.9 in 1020 steel. So we can look at a little bit more hardenable, a 0.9 manganese, which would be on the high side of the chemistry. And we can see that our DI changes very slightly. It goes up to about 21.4 or 21.5 millimeters. On the low end, we can look at the change in manganese here to from 0.3. And we can see that lowers the DI here to about 12.17. So about 12 millimeters or so to make that 50% martensite in the core. Let's go back to the 0.6. And we can plot this again, and we can see we're back at that 16 millimeter bar. Now, let's say we have a little bit more carbon. So I believe 0.23 is the high end of the chemistry scale of 1020 steel here. And we can see that has a little bit of an effect here. When we go to the 0.23, we have a DI that's increased to almost 17 millimeters. So about the same when you play back and forth with these manganese and carbon levels here. I believe I had 7.17. Yep, that's correct. Is the low end here. And so this would be a really low carbon here. And we would expect that the DI would be a lot less. And we see that this is about maybe 14 millimeters. So we can play around with the different chemistry levels and carbon levels, depending on what version of melt that you have of 1020, and you can see the hardenability or the DI calculation from that. Going back to the presentation here, we also have explore a little bit of effects here for the Jominy end quench. Now the Jominy end quench uses a 1-inch round bar that's austenitized, and then it's water quenched at one end. There's a bunch of standards that are involved with that, like a 1/2-inch orifice for the water quench, and it has to, be about 2.5 inches tall for the water column. But the Jominy end quench is really great because it gives you a bunch of cooling rates versus depth from the quench end, and it's used to predict the hardness of an as quench part, and better to gain an understanding of the material's hardenability, because you can see what kind of phases and hardness you can get per that cooling rate, basically from the Jominy quenched end here. And so we do have the Jominy predictor here, and I didn't close it this time, so that's good. And so we can go right to this Jominy utility here. Again, we picked the steel that we're going to use, and it's 1020 steel here. Same modifications that you can make. And we will run this simulation to see the changes in chemistry and stuff that can happen to the Jominy points. Now these are all specified as Jominy point down the list here, and we can see at the surface our hardness would be about almost 50 HRC due to that water quench, and then it quickly drops down to about 20 or so in the core here. We can also look at the different phases that are present. So we can select the phases based on the Jominy end quench here, and we could see that either at the surface here, we have a little bit of martensite that's formed, about 62%. And then we have a little bit of lower bainite and a little bit of perlite that's formed to figure out the balance here. As we go deeper into the bar, the quench has less of a severity, lowers cooling rates. We can see that these phases convert back to like perlite here and then ferrite until we get down to the end of the bar where it is just for ferrite and perlite. And this is basically the reason behind the hardness that we see. It goes from martensite at the surface to ferrite and perlite in the core here. Now that we've done that, let's take a look at the differences in chemistry changes. Here we have the higher end of the carbon. We can take a look at what that would do. And the higher end of the carbon produces a little more martensite at the surface. You can see that shift up a little bit here. We're about 44 HRC at the surface from that, a little bit of extra martensite. And it goes a little bit deeper in, but again, as we go deeper into the depth from this quenched end, we go back to ferrite and perlite as that's a slower cooling rate here. We can go to the lower end as well on carbon and plot that. And we can see we have a lot less martensite that's formed here. We have probably about 32, almost 33 HRC, somewhere between those as far as the hardness on the surface. And then as we go back to the core again, we drop down in hardness very quickly. So we'll go back to the 0.2 nominal carbon, plot that, and then we will look at changes in manganese now. Again, we go to 0.9 on the manganese, which is the high end. And we can see we increase the hardenability much like we did with the carbon here. We have a lot more martensite at the surface, about 86%. And then the actual hardness at the surface is about 45, 46 HRC. So you can see with these nominal, these chemistry changes, they really play an important role as far as the hardness that you can get from the higher end, the higher quench rates. And then the lower end quench rates are not as changed because they still go to the same kind of phases here. With the manganese at 0.3 here, we can see that we drop martensite very quickly at the surface here, and it's mainly perlite and ferrite that dominates. Okay, so we have a good idea of cooling rates and a little bit of the chemistry changes on the DI. Our next steps would be to look at the alloy composition on the TTT and the CCT diagrams. And for a lot of people, this is a lot better visual representation of what is happening. When the materials get more hardenable, the TTT curves shift over to the right, and so you can quench a little bit faster here and miss the noses of these different phases. The time temperature transformation or deals with isothermal holds. So if you're holding down here, you can see the plot here. We can expect to start transformation to bainite if we held at 400. At about a 1 second, we can see the start transformation, and then like 90% complete is somewhere along this 400 seconds here. Oh, sorry, this 21 seconds here. And then for the continuous cooling transformation, or the CCT, we can specify cooling rates so you can see the cooling rate and then see if you're missing the noses or whatever for transformations. You'll notice that the TTT diagram does not have martensite transformation. It's because it's the isothermal nature of the bainite transformation there. And then the martensite would start directly below that. You can see that on the continuous cooling diagram. These really help to gain an understanding of the boundaries of which different phase transformations with respect to time. And it's really a good way to visualize hardenability changes. So we will open that up. I did not start that one, so let me do that real quick. Bear with me. There we go. You can see these happen really, really fast. These open up really quick, and you can get these results really fast with what we're doing. So again, we picked the material 1020 steel. We're going to leave everything kind of nominal the way it is. We can set the upper and lower bounds. I'm pretty good with these. And as far as a TTT diagram, we have some controls over whether you want to do temperature or time in seconds or degrees C. And then there are all tempering kinetics and different things to control the resolution of the plot here. But we're going to start with the default and take a look at the TTT diagram plotting for this. And so we don't use the TTT diagrams directly when we use our phase transformation kinetics. These are all rate-based calculations. And so this is just a visual representation of what that rate-based equation would output given the temperature holds and everything. So I'm going to go ahead and select ferrite and perlite, bainite for the TTT diagram here and plot these. And we can see that's very similar to the one that we saw in the intro. We see a little bit of the ferrite range up here, the noses, and then more of the perlite ranges here. And then we see the bainite transformations here. So if we were to cool down to 400, you can see we have the same kind of data here. We would expect to start around 1 second and to finish around 20 or 30 seconds or so. So we can see the effects of the different hardenability things. So we can choose, again, 0.323 carbon. We can analyze that. Oops. We can analyze that. And then I'm going to shut off the auto scale so we can actually see these shifts move. We can go ahead and plot that, and we can see that the carbon with a little bit extra carbon shifts the diagram a little bit to the right here. Not exactly very significant, but if we were to go up to say like 0.3 carbon, we can see a big difference in the shift in the TTT diagram to where the starts are and then where the ends are. So this is very important to get for your chemical composition. Again, if we go to the lower end of the carbon range, we can see a plot where you'd have to quench within tenth of a second here, kind of to hold and to get it to start right away for the TT diagram for the ferrite and perlite. The next thing we can do here is a 0.2 carbon and get back to where we were. We could look again at the difference in manganese. Here to the 0.3, the lower end, and it has kind of the similar effect as what we saw with the carbon. We can see that has a more significant effect here within that range. The 0.3 is the low end of the 1020 steel here. We can see that really brought it to the end here. And then we can see at the high end range here, we can see the diagram shift, and we can see that it's a little more hardenable here with the higher end manganese. Another thing we can look here is go back to the default, and we can look more into the CCT diagram. We'll just go ahead and replace it. And we can plot this and choose bainite, ferrite, perlite, martensite, and update the plot here. We can see basically on the cooling rate, we have shortest cooling time and longest cooling time. We can see the number of cooling curves. We can apply cooling curves to the graph to show the shortest and longest cooling time here. And you can see if we were to quench through here that with the shortest time, this 10 seconds, we will definitely hit the ferrite and perlite here, and we will hit a little bit of the bainite before we hit the martensite here. We can shorten this. Let's say we have a slightly faster cooling rate here. We can see that the diagrams begins to show a little bit more, and it really gives you a good idea of how fast you would need to quench for that. You can specify a cooling rate here. We can say this is 10 degrees C per second, and we could have your own user cooling rate applied to that. Let's try these. Of course, it's not working right now. That's right. So let's look at the differences here in the chemistry. So we can look on the low end of the carbon, and we can see how it shifts the diagram. We can see that we hit a lot more of the perlite range here before we end up getting to the bainite and martensite ranges. And then we can do the same. We go back to nominal. We can look at the higher end of the manganese content here and plot that out. And we can see that we're starting to miss a little bit of the nose here, and we're getting a little more of the bainite and the martensite as we cool through these processes. If we will go very slow, we will expect to basically create all ferrite and perlite. Very good for machining and stuff like that. So depending on what your application is, you can get a good understanding of the hardenability of the steel through these little simulation tools here based on chemistry changes. All right, so with that visualization in mind, we can start looking not so much at the chemistry here, but a little more into the process variability. And for that, we're going to use Heat Treatment Process Simulator, or HTPSim for short. So the HTPSim will let you model the thermal processes or chemical processes so that you can adjust those processes and improve them. So what we're going to work with today is a real simple process. We're going to heat up the 1-inch cylinder bar here, and then we're going to hold for a short amount of time here. There's going to be a little bit of an air transfer, and then we're going to go with a water quench and then an air cool to get everything to 20 degrees C. So that's described in the example process here. And then the variations we can look at here is the transfer time. So up here, we're going to see a little bit of change when we adjust the transfer time. We can also look at the quench agitation, so we can go a little slower, a little faster on the HTC that we have. And we can see the sensitivities basically on that. We're going to look a little bit at the quenching temperature, and then we're going to explore some alternative processes, whether, if quenching in water wasn't sufficient, maybe quenching in oil may be good, depending on the application. So if I go to HTPSim, we can see there's a lot more buttons and stuff to push here. So we go to the 10 series steel, 0.2 carbon again. Again, we have the different chemistry options and stuff like that. And this time we actually have an initial phase composition here. So we're going to assume that it is 50% ferrite and perlite, more in the kind of the neo condition here. For the geometry, we're going to have it just to be a 1-inch cylinder. Um, so then millimeters, that is 12.7 for the outer end diameter and 0 for the inner. And then as far as process, we can start to build our process here. So we are going to insert a step afterwards, and it's going to be a thermal step. We were going to use furnace heating. And 2 hours should be more than enough for the heat up and hold. With HTPSim, you're allowed to use some customized equipment. You can either manually input a lot of the HTCs and stuff for this, or we have in our database example options that'll get you pretty much in the ballpark, and then you can work from there. We're going to use this heating furnace ABC here, and we are going to heat up to 850 degrees centigrade. So it's the ambient temperature for the furnace, and then the HTCs are automatically applied by selecting the heating furnace. As far as controls, we have a lot of options. None of them are really great for what the work we're doing here today, but we can do tempering. We can do the carbon and nitrogen effect and volume change. We can do carbide decomposition modeling or latent heat if you're working with like bulky parts that have some transformation, bulk transformation. This is really important. We can do alloy carbide precipitation, austenite grain growth, and carbon partitioning models. Again, for the low alloy steel that we're working on, the simple example, none of these really apply very much. You can also affect your output frequency, and this basically is it shows every 10th increment. It'll show the results of that. So this is really good for computational speed. To be honest, this is pretty much the resolution that you would run on. You really wouldn't want to go much lower than that. We also have unit selection. You can choose between HRC or Vickers, depending on what you're working with. We also have temperature in degrees Fahrenheit or Celsius. Time length, we can do minutes or seconds. And then length, we can do millimeters or inches, depending on what units you prefer. So we have our furnace heating step set up. We're going to insert a step afterwards, and this will be our transfer time. We're going to start with a 15-second transfer time. And we will just use the heating furnace HTCs, but we'll use a film temperature if the part is at 850 degrees and 20. So we're looking at about 430 degree film temperature that the part will experience as the ambient temperature. And to insert a step afterwards, we will do the quenching. This will take about 900 seconds here. We'll do a water quench. And we will choose our water quench HTC, and the water is set to about 20 degrees C for the quench. We can see the HTC was automatically applied. It's about 8,000 watts per meter constant for this work that we're doing. And then finally, we'll insert a set afterwards. And this one, we can go with just about an hour. Known from experience, it's kind of already at that temperature, but it's good to do, air cool. And then we'll choose the air cool temperature and it's set to 20 degrees C. And then here's the HTCs for that. Okay, so we have our process steps fully defined. We have our material fully defined. Only thing left to do is to analyze the process and save this to the temp directory. Okay, and it's done. So we can go in the plot here, and the plot initially just shows the temperature over time. So you can see to make sure the part reaches the temperatures. This is for a surface node here, so we can see that we heat up rather quickly, and we get to our temperature here, and then we have a transfer, and then the water quench. For that, we can choose the single point where we're choosing the outer diameter. We could also do the same for the inner diameter here on the list, but what we're looking for here is the single increment. We want to kind of see the results, and so this will show us the results at the end of the process with the XY axis set to the depth from the outer diameter. From here, we really want to kind of look at things like hardness and phase volume fraction. We could also look at the carbon and nitrogen content, iron carbides if they're present, alloy precipitates if they're present, and then carbide size or grain size throughout the cross section of the material. So it's just different outputs that we can have. I'm going to choose phase volume fraction. And I'm going to select all the phases so that we can see what phases happen through the traverse of the part after the process here. We can go ahead and hit plot here, and we can see that With the water quench at the surface, we have a pretty high hardness here of about 42 HRC. We can see as it continues through the cross section of the part here, the hardness drops again, kind of like the Jominy we were looking at. The martensite that is formed is roughly about 70% or so martensite right at the surface, and again that drops kind of with the hardness here. We can see that there is a little bit of perlite, upper bainite, and lower bainite that's formed near the surface as well to kind of fill out the balance. And we can see as we go towards the core, the perlite again dominates the core reaction here. We can see the core hardness here after the process is something along the lines of about 21, 22 HRC. So there's a big difference between the surface and the core as far as hardness, kind of a big gradient there from the water quench. We can explore a little bit of the hardenability changes again with chemistry here. We can look at the total carbon content change, and we can see the changes from that. We can see with a little more higher carbon, we are a little more hardenable, so we form a little more martensite, and we get to almost about 45 HRC at the surface here. But it doesn't really change very much as it goes through into the core because the cooling it's slower here. We can see we still at 24 or 23 HRC. We can go back to 20 and get back our results. And again, we can look at the changes in manganese as well. So we can go down to like 0.3, which is on the low end here. And we can see that has a big significant effect here. We form a lot less martensite right at the surface here. And our hardness at the surface is only about 29 HRC or so. So this is a lot less of a gradient through the part. So if the hardness is the issue, you can adjust your chemical composition to fit whatever application that you would have. But what we're really kind of looking for with HTPSim here is process variability, because we already kind of looked at the chemistry variability here. So we go back to the defaults here, and we can look at changes in the process. So one of the easy levers to pull is the step time. The step time for the transfer. So if we look at maybe doubling the transfer time, about 30 seconds, we take a little bit longer to get the part transferred from the furnace to the quenching tank. And we can see what that will do. And kind of non-intuitively, it also increases our hardness a little bit. It gives us a little bit more martensite here right at the surface. The core property, again, is largely unchanged. It's still about 21 HRC as far as the hardness. And we can see the ferrite and perlite pretty similar here. We just have a little bit more martensite at the surface. So like I said, it's kind of non-intuitive. You can kind of look into the process to understand what is going on to create that. And through the data and the settings here, the outputs, we can not look at the end of the process. We can look at the end of the transfer step. And what we're really kind of looking for is the temperature. We can leave phases on, that's fine. So as we go into quench, because of the longer transfer time, we have about 803 or so degrees Celsius at the surface, but the core of the part is still a little bit hotter, and it's about 812. So it basically sets up this temperature gradient here. And so this is the lower temperature going into the quench, and it's the surface. So it quenches a little bit faster, and so we get a little bit more martensite at that surface. And that's kind of the reasoning behind that. If we go back to the end of the process here, we can look at the different quench rates as well. Let's go back to the 15-second transfer time and plot that, and let's change temperature to hardness. Excuse me. There we go. And we can see where we were back to where we were with the about 42 HRC at the surface. So we can look at the water quench temperature. You know, if we quench it at 20 degrees C, say we wanted to, our temperature is a little bit higher, and we can see what the difference is with a 30 degrees C water quench. And you can see the changes very slightly as far as the hardness here. We can see the martensite went down a little bit from the little bit higher temperature of the water. We could also look at agitation. So we go back to the 20 degrees C here and plot it. We can look at changes in agitation. Let's say we have shut the agitation onto a lower speed or shut it off. We have a scaling factor for oh, this is on the air cool. Almost got me. We can see the the agitation on the machine could be set to a lower speed, so we can basically just scale this HTC to see if there's a big sensitivity from that change in heat transfer coefficient. And we can go ahead and plot that. And we can see that that change in agitation for the HTC really dropped the hardness here. So we have less of a gradient from the surface to the core of the part here, with 33 or 33.5 or so HRC at the surface. You can see that dramatically changed the amount of martensite that was formed. And that's really the thing that drives the hardness for this application. Again, we can look at maybe the high end of this and see what a higher agitation. Let's say you have a button that can go a little bit higher flow rate. We can see what that might change here, and we can see that it has a pretty dramatic effect. Again, we form almost about 87% martensite because of the faster cooling rate that is provided from that HTC. And we can see that the hardness here is about 45.5 Rockwell at the surface. It doesn't really change too much again to the core. We're still about 22 or so hardness. It really affects mainly the surface or the heat transfer rate would be a lot higher. And then the last thing we can do is we can look at different actual applications for the processes. Instead of doing a water quench, you can explore what would happen if you were to use oil quench for this type of application. Instead of transferring to a water tank, you transfer to an oil tank, and you're interested to see what happens there. So we'll go back to the one scaling factor here, and we'll use the oil quench tank HTCs that we have in the Dante database. In 65 degrees, we can start with that and see where that goes. We will analyze that, and we can see that it has a very big effect. We can see we're no longer really forming too much martensite on the surface. We have mainly upper bainite and perlite that is formed from this lower cooling rate from the oil quench process. And we can see we end up here now with the 25 HRC at the surface, which is much less of a gradient from the surface to the core as far as hardness. So if that's what you were looking for, then this would be maybe a good application, or if maybe that doesn't meet your requirements, you'd have to look into a couple different other changes, like quenching temperature and stuff like that has larger effects. Again, you can go through and look at the multipliers with agitation rate and stuff like that. And so there's a lot that you can do, and with these little modeling tools, you can really knock out the initial work and then see what quench rates will work really good for you and what your application is very quickly. All right, so that is the last HTPSim that we had here. Last thing I had was a little bit of a case study on the effect of chemistry changes on 8620 steel. This is a paper that Stefan and I wrote back in, I think, 2019 when we were still at Cleveland State. And it worked really good because they had a really good process to define as far as carburization, and it matched really well with the data that we used. But more importantly, for the application we're looking here, there was a high and low chemistry rate. After we did the initial designs here, we tried to look at the differences in the chemistry. So you can see that the nominal is very low chemistry. It's really close to the low chemistry end for 8620 here. And while this is in a low hardenability steel, it still has some pretty good applications for what we're talking about. And then the high chemistry rate here, we can see is a lot higher than what the nominal was that they were working with. So we can see the effective chemistry variation on the part. Again, we can go through the same kind of steps that we did with the 1020 here. We can see the chemistry changes here, low chemistry on the left and then the high chemistry on the right. And we can see the higher carbon and chemistry values here shift these perlite and ferrite and bainite curves pretty far to the right here. Instead of tenths of seconds, we're actually 1 second or so before these transformations actually occur. The low chemistry has a very significant difference in DI as well. You're looking at about 28 or so millimeter diameter bar that can be quenched for 50% martensite, and whereas the high chemistry has a big difference, is about 62 or so. It's almost twice, a little more than twice the diameter bar that can be quenched there. So there is a big significant difference between this range, and depending on where your material is on the range, you can expect a very big difference in the hardenability of your part. So this one used tensile samples, so we used a little bit of an eighth of a geometry here, so we halved it via symmetry, and then we used quartered to reduce computational time. And we can see the difference here with the phases with this path plot here. We can see we have about 86 or so percent martensite where the carbon is high here. That is the rest of the balance here is retained austenite. This was not tempered. This was just as quench condition, if I recall correctly. And we can see the differences here are mainly really in the low nominal and high alloy in the core of the part. So the carburization really helps to make the case more uniform, and so the differences in chemistry really don't have as much an effect as it would do in the core here, where the carbon is low. So the carbon really kind of drives this. We can see that the nominal and low alloys are really close to each other here, and like we saw with the chemistry ranges. And then in the core, we can see a lot more martensite being formed from the high alloy. And then likewise for the retained austenite, we can see that the high alloy has a little bit more retained austenite throughout the core, but mainly because of the difference in carbon. And this is a very thin cross section, so it quenches pretty quick. The core hardness, again, is affected more than the surface here. Again, this is really driven by the carbon case. So if you were going to be carburizing your lower hardenability steels, you would expect that the carbon in the case should keep things a little more uniform, depending on the alloy composition. So again, the core here, the hardness is a little bit higher from a little bit more martensite that's being formed from the high alloy, and the nominal and the nominal kind of lay on top of each other here as far as the hardness. And the last thing we have here is the effect on distortion and residual stresses. So the variations are affected by the initial microstructure, the volume change, carburizing, and the quenching conditions. We can see through this plot here, the residual stress that was predicted for this is pretty similar again for the low and nominal alloys. But the high alloy has a little bit less compression and a little bit less tension here through the core, and really kind of shows the martensite transformation that happens. There's a little bit more martensite here, and that kind of helps pull the surface here a little bit more into less compression than it would with the low and nominal alloy. We can also see the difference in the axial distortion, so the length of that tensile specimen changed based on the low and nominal or high chemistry. Low and nominal, again, is really close, about 11 microns or 14 or so microns for both of those, but the high chemistry had a little bit had more martensite, so it grew a lot more, about to 34 or so microns, so almost twice that as far as the low and nominal chemistries. And the residual stress here again is basically based on the phase transformation timing. So when that phase transformation occurs, it pulls that surface into a little bit less compression. And that is all that we had for today. I believe we should be good on time. So if you have any questions, I would love to answer them. You can put them in the Q&A section of the meeting here. And if I can get to it, I can see if there's any there. Q&A section. Okay, yeah, you can go here and you can start a discussion here, or you can ask a question if you would like. And I'll give you a couple minutes to do that if you'd like. But if you don't have any questions immediately, you can always email us at support@dantesolutions.com right here. Or we have a lot of different case studies and stuff on our website. You can check that out at dante-solutions.com. You can do /publications and see all the publication work that we've done. And there are some case studies and animations and stuff that you might find interesting for your processes. Or give us a call at the office. Give it about maybe one more minute here if there's any questions.
Hey, Jason, looks like someone raised their hand.
Uh-oh. I don't believe Raising hand works. Sorry, Gopal, you might have to use the Q&A because might. Oh, I can. I can allow Mike. You are hot mic'd, Gopal. You still as
Hey, Jace, I couldn't send any message in the chat because the chat was turned off for the meeting.
oh no.
And that's why I couldn't, the mics are muted and the chat was closed.
Oh, I must have not checked the box. I'm sorry, everybody. That's my technical issue there.
So that's why I used the hand raise to get your
Yeah, I
attention.
appreciate it. Thank you for letting me know. So if you guys
Okay.
have any questions, please email me at support@dantesolutions.com,
Yeah.
and I can answer any of those from there. Did you have a question, Gopal, while you're?
Yeah, I did. In fact, the HTPSim is really interesting, but I didn't know whether it is only useful for simple shapes or you can custom import a shape.
So it is used for simpler shapes. We build the FEA model in the background to make it more simple.
Okay.
But you can simplify things down to a ring or a cylinder geometry.
Okay.
And a lot of those have, you can use those pretty much for a lot of different sections on parts. And then you can run it from there. But in order to simplify the calculation, we use just the cylinders or ring shaped geometry.
Okay, that's awesome. And then I remember in the HTPSim you tried modeling a 1-inch diameter bar, right?
Yes.
But then all the properties appeared to go to was it 1 inch or was it 12 millimeters?
Well, that was the radius. 12.7 radius is half inch radius, so 1 inch
Okay.
diameter.
So
Yeah.
it's a 1-inch diameter bar went to the half inch. Okay, that's great.
Yeah.
Yeah, I'm surprised at the models having that many. I mean, the small change in chemistry having that large effect. Okay.
Yeah, with
so,
low hardenability steels, this is a very hot topic as far as the effect. You do have less of a issue as you go, as you saw with the 8620 stuff. The little more hardenable steels.
Can you also predict decarburization in any of these models?
Yeah, we can set that up as a carburization with a lower carbon potential, and then the decarb effect will show.
Okay. Or a decarburization cycle.
Yeah.
Okay. And this is a harder question. So generally during heat treatment, we also put a stop off to mask certain areas. And
Sure.
I didn't know if there was a way to actually do that. Simulate
for chemical,
in some way.
for the HTPSim, no, but for the full FEA package, we can do that definitely. We would just discretize that surface and we can set it to have no carbon or whatever transfer through that.
Okay, excellent. Thank you. I mean, you're a
Yeah,
great
thanks for the
teacher.
questions, Gopal. Again, sorry
No,
everybody for the technical difficulties here. Next time I'll make sure I definitely click that button.
You're
That was
an
my bad.
excellent teacher. Thank you. Yeah, thank you again.
Oh, we do have a Q&A. Oh, as far as ice water quench or liquid quench, I don't believe we have an HTC for those. We use basically the general HTCs as far as cooling for those whenever we model those processes. And a lot of times it's just setting the ambient temperature that we quench to. So for like an ice water quench, it would be a higher low temperature than the liquid nitrogen quench, which would be a lot lower temperature.
Yeah, I think Dante does have HTC fitting. So if you have temperature experimental data from some couples using ice water, then we can calculate the HTC quickly using a tool called HTC fit.
Yeah. Good point, Charlie. Thank you for adding that. Here's the application of HTC fit. While we have it here, you can do your experimental data and load it in, and you can. This will help you fit the data for those HTCs. One new post. Oh, so I've been measuring the HTCs with different temperature plots. We use standardized probes. A lot of times when we do the work, we use thermocoupled actual parts that the people are using in process. And we have thermocouples embedded under the surface or in the core or whatever for that actual process or that actual part. We could also we've developed a couple quench probes over the years to measure the furnaces and stuff like that, the HTCs of them as well. So we can use standard probes or even custom designed probes for that. You could also use some CFDs programs you can use if you have a really good trusted analysis. You can get the heat transfer coefficients from CFD as well. So those three methods usually are really good for that. Thanks, Noah. All right. If there's nothing else, we're looking pretty close to the time here. Give it a couple more minutes. It looks like the chat's working now. Maybe one of my colleagues enabled it for us. Oh yeah, right. With at least 2 HTCs, right? Charlie added in there one near the surface and one near the core, and this way we can help get the changes in conduction as well as the heat transfer coefficient for convection as well.
Jace, this is Gopal again.
Hey, Gopal.
How do your customers use the TTT versus using the CCT? Which one is more practical, and why are we using TTT at all?
Well, the TTT is really useful for the isothermal holds if you're going to be doing like an ostempering or something process. And then the CTT will show you the cooling. So they each have their own merits. And again, they're really good visual representations of the changes in hardenability too, based on either chemistry or what you're using. So they each fill their own little niche in the market there.
Oh, okay, thanks. And if I wanted to calculate the rate of martensite growth over cooling time, is that possible in HTPSim?
No, the growth, the volume expansion would be more of the FEA application there. Since we don't model the distortion or residual stress with the HTPSim, it's just a thermal process calculator.
Yeah, another tool. Sorry for the interruption. Another tool, Meta Simulator, can also describe it.
Yep, that's another good one. MatSim will have the transformational strains.
So normally before we run complex parts heating and the quenching process, we check the material properties through MetaSim. So that's the kind of standard procedure we take. Maybe you can use the rate-based, Jason. That will be simpler.
Yeah, probably.
Yeah, or you can import like 1,000 of data lines that can work too. So.
Yeah, right. You can load your data if you have your time temperature data through there. Let me just load an example here. Mat simulator and rate temperature input. All right, then we can analyze this. Oh, it still thinks I'm in the directory. 1 second. Doing it live. We can plot that, and then through here we can see temperature and strain. We can see we have the heat up, we have the transformational strain, and then the transformational strain here. Great, let me check to see if there's any more questions. It does not look like it. And we're close to the end of the hour here. So I want to thank you again for attending the webinar. Hopefully you find everything valuable. And then if you have any more questions, go ahead and email us at support or check out our website. We have a lot of good answers and everything there. Thanks again. I'll see you in a couple months with our next webinar.